going to start with a brief introduction of, again, zero forcing equalizer. Then once we finish this, we will be discussing about the other type of linear equalizer, which is MMSE equalizers. And then the final one, which is your adaptive equalizer for linear equalization. So these three are your different types of linear equalizers which are there in your syllabus. So starting with, so now how this or why this MMSE equalizer is needed, we have already discussed this just now, that MMSE equalizer is needed. Why? Because zero forcing equalizer focuses only on ISI removal. It does not consider noise removal. So actually, zero forcing enhances the noise. It does not remove the noise. So MMSE has to overcome both the ISI effect as well as the noise effect. So it performs better in noisy channel, whereas zero forcing performs better in noiseless channel. So this is what the condition was, that zero forcing is useful in noiseless channels, but in noisy channel we would prefer to use minimum mean square error equalizer. Now we will go through the detailed process of the MMSE equalizer, how MMSE equalizer is actually used, and what is the mathematics or what are the steps involved in doing this equalization using your minimum mean square error equalizer. So the first step in generating the output of this equalizer is, first step is to gather the received signal. So received signal, what are we gathering? We are transmitting pulses. So like I have discussed in your intersymbol interference, that diagram, if you remember, so the diagram was having symbols here. We are passing symbols here, right? So we have multiple symbols which are being propagated with respect to time. So here time was there, and this is my symbol duration. So this is my transmitted signal or baseband signal. So this is my time duration of each of my symbol in digital data communication. That means I'm transmitting a symbol 1, 1, and 1. So this is digital 1, 111 actually, that I'm transmitting in the communication channel. Okay. So what is the risk? So this is my transmit actually, and when I'm passing it through the channel, then output of the channel that is being received at the receiver would be multiple components. Previously, I have already told you that every signal that is passing through this channel will experience certain amount of multipath effect. Multipath effect means it will have some amount of reflection, it will have some amount of scattering, it will have some amount of diffraction. So all these effects will be added up. And what are they causing? They're causing multiple copies of the transmitter to reach in multiple time duration or different time duration at the receiver. So there is delay there. Okay. Each of this transmitted signal will reach the receiver in different time instances because they are traveling different time duration. Okay. Okay. So the multiple copies of this transmitted signal will reach the receiver. So multiple copies means I will have one signal for the symbol which is at y of k. This is my one signal. Delayed version or the previous version of the signal would be k minus 1. Another signal would be k plus 1. So all these are different versions of the same transmitted signal which are reaching the receiver at different time duration or they're traveling different path length because of this multipath effect. Okay. So what is my received signal here? Received signal is nothing but a combination of all the different components of this received signal at the receiver side. Okay. So you can see here we have a current symbol as yk, previous symbols as yk minus 1, yk minus 2, yk minus n. So suppose if this is my actual transmitted signal dk, so this would be my previous transmitted signal dk minus 1, this would be dk minus 2. one step before this. Okay, so if this signal is received at the receiver, this would be yk, this would be yk minus 1, and this would be yk minus 2. So like this, it is being demonstrated here. So different types of signals will be received for the same transmitted signal here. So now the current received signal is yk, but previous received sample signals was yk minus 1, yk minus 2, and yk minus n. Why am I concerned with the previous samples, the previous symbols here? Because of the effect of inter-symbol interference. What is happening? One symbol is overlapping with the next symbol. So this is overlapping the next one, this is overlapping with the next one. So my current symbol, that is your yk, the current signal that is being transmitted, will have some component of the previous symbol as well. Why? Because it is overlapping. Okay. So it is overlapping. So it is overlapping here. So some part of your current symbol will have the effect of previous symbol because of ISI or delay. How? So if I say that this is my previous symbol yk minus 1. Okay. So this yk minus 1 is overlapping with your current symbol, which is your yk. So current, I am transmitting currently this symbol, but I have this receiver at the receiver because the previous signal is already delayed. Because of this multipath effect, this ISI will cause the signal to interfere with the nearby symbol that is being transmitted. So this overlapping that is being done here, so if I change my ink color, so the overlapping that is happening here between the previous symbol and the current symbol is actually the inter-symbol interference. So at the receiver, I will have interference of the current signal with the previous symbols that is being transmitted because of multipath effect or multipath channel leading to ISI. So I will have all my components here in the receiver side leading to ISI. So what is my actual received signal that is there at the receiver side? We are receiving the current signal that is being transmitted along with the previous delayed version of the transmitted signal. Delayed version means k minus 1, k minus 2, like those symbols. So this is my current k and this is my delayed version. Along with this, I will have some factor which is called your noise here. What is noise? Noise is your unwanted signal which is present in the wireless propagation. Okay. So second step is to calculate. So first step is get your received signal. Second step is to calculate the weight of the equalizer. What is weight? Weight of an equalizer is nothing but the multiplication factors. What are these multiplication factors? These multiplication factors are nothing but the factors using which we are going to overcome the effect of the channel. Okay, so to overcome the effect of channel, what we are doing, we are selecting certain multiplication coefficients or factors which we will multiply the received signal with to overcome or to negate the effect of the wireless propagation channel or multipath effect, or in short, the intersymbol interference. Okay, so what are these factors called as? We are calling these factors as weights. So W is the factor here, and we are using one matrix which is consisting of all the coefficients or all the factors here for each of the symbol. So suppose for your current symbol yk, we are multiplying the weight. The weight is W0. Yk minus 1, we are using the weight W1. Yk minus 2, we are using the weight W2 here. Okay. So we are deciding on a certain set of weights with which we will multiply the components. Okay. So what are these weights? These weights are going to adjust the output such that we can regenerate the actual transmitted signal. Okay, that is my objective, to minimize the error between the received signal and the transmitted signal. So now equalizer output for MMSE equalizer will be calculated. So how it is being calculated? We are going to multiply the weight with the received signal components. So we are simply going to multiply this. Okay. So this is my regenerated output at the equalizer output. Okay, so this is my regenerated output at the receiver side. So the equalizer is generating this output corresponding to the actual transmitted signal, which is your decay. So equalizer is generating decay cap, but the actual one is this. So what is the error? Error is nothing but the difference between the transmitted signal with the equalizer generated output. So the equalizer generated output is decay cap. So this is my error that's going to be calculated for your MMSC equalizer. So what is the error signal here? Error signal is nothing but simply this equation. This is what I have written here. So this is my actual transmitted symbol. This is my estimated or equalizer output, and this is my estimation error. What is estimation error? Error is the difference between the regenerated output with the actual transmitted signal. Okay. Our goal for MMSE is to minimize this error as much as possible so that the actual signal and the transmitted and the estimated symbol is almost the same. Okay. So we will calculate the mean square error from this error function, and we will try to minimize this mean square error value. Okay. So we are taking the square of the error. Why? Because taking a square means we are trying to minimize both the positive and the negative errors here. Okay. So any kind of large errors, we are going to take the mean value so that large error can be multiplied with or compensated heavily with a larger value of coefficient. We can multiply it with a larger value of coefficient. Clear? So we are trying to minimize this mean square error factor here. So for minimizing this, we are going to use one optimization condition here. That is to optimize this weighting factor or weighting coefficient here. The MMSE uses to minimize this error factor uses this relationship. Now this is an optimization rule which is used here. It consists of two parameters. One is called R inverse and the other is called P or small p here. So what is this capital R basically? This capital R is nothing but the input autocorrelation matrix. Autocorrelation matrix means what? That means it is a factor which is calculating how much the received signal is actually related to each other. That means if I am trying to calculate the similarity between the transmitted symbol yk and the previous transmitted signal yk minus 1. So I'm trying to calculate the similarity. Correlation means what is the similarity between these two factors here. Okay. So similarity means I'm trying to see how much of these two factors are same as each other. So I'm trying to extract some information amongst them. So we are trying to see how much the received samples are related to each other. Okay. So we are trying to get this analysis from the received signal. So capital R is autocorrelation function between the received signals. So yk will be related to yk. So this factor would be very, very high. Relationship of yk with yk minus 1. That means just one symbol before this actual transmitted symbol. What is the correlation between them? So if there is high ISI, so what I'm trying to say here is, suppose this is your yk minus 1. Okay, this is your yk minus 1 symbol, this entire duration. Now what is your yk then? So if I just change my ink color, okay. So yk is suppose this. So this is your yk, actual transmitted or the next transmitted signal. Now correlation means what? Correlation means how much is it overlapping with each other. Okay, what is the common factor here? That is what is correlation here. Yeah. So what is the common factor here is the overlapping factor. So if I have larger ISI or I have more intersymbol interference. More intersymbol interference means more is the amount of overlapping. Less intersymbol interference means less is the area of overlapping. So this autocorrelation function or the value of R is nothing but how much is the intersymbol interference between this received components or received symbols. That means if the autocorrelation function value is smaller, that means ISI is smaller. If this is larger, that means this is larger. So what is this estimate here? We are trying to estimate if the intersymbol interference is more, then how we will optimize this in the coefficient value. Okay, how we will change the coefficient value according to this intersymbol interference value. Clear? So this is my first factor, which is your autocorrelation function. Clear? So this helps you to understand how much is the interference and what is the level of interference and how we should be optimizing your weight factors in the equalizer equation. Next, we have a factor which is called P. Now P here, so first factor was R. So the R factor was actually calculating the autocorrelation. We are calculating the autocorrelation. Autocorrelation means same signal, received signal. We are just comparing the symbols from before and after. Just simultaneous symbols which are being transmitted, we are just comparing them. But in terms of cross correlation, what is this P factor? P factor is cross correlation. Cross correlation means I am transmitting the symbol dk, but I am receiving the symbol which is yk. Okay. So I'm transmitting dk, but I'm receiving yk. That means what is the relationship between the desired signal and the received signal? So here, cross correlation factor, what it is trying to tell, or why are we using this cross correlation factor? We are using this cross correlation factor to understand that what is the common factor, or how much is my received signal similar to my actual desired symbol. So I'm transmitting a symbol 1, but I'm receiving a symbol 0. Then what would be the relationship? Is 0 equal to 1? No. So the cross correlation factor would be very, very low. Very, very low means my received signal is not same as my transmitted signal. So this factor is trying to compare my received signal with the transmitted signal, and it is trying to convey that whatever I have received is not what I have transmitted. So the equalizer has to optimize the value of the coefficient accordingly. So there are two factors here. One is the intersymbol correlation, which is what is the amount of intersymbol interference that I am experiencing in the received signal because of this multipath effect of the channel. Next factor is your cross correlation. Cross correlation means I am transmitting a signal, but I am receiving a different signal. So at the receiver, what is the received signal and how much is the difference between the received and the transmitted signal? That error actually is your cross correlation factor. So capital R is a measure of ISI. Small p is a measure of the error, or the difference between the transmitted and the received signal. Clear? So if I am using capital R, I am trying to overcome the value or overcome the effect of ISI. If I'm using small p, I'm trying to overcome both the effect of ISI as well as the effect of noise in my received signal. So using these two factors, combination of these two factors, I'm trying to optimize my coefficients that are used for MMSE equalizer. Now here this is the basic understanding of MMSE equalizer. From here you can understand that MMSE equalizer is far more advanced compared to your zero forcing equalizer. Zero forcing equalizer was focusing only on reducing ISI. It was not focusing on reducing the error factor. Error means the difference between the transmitted both the ISI as well as the okay. So this is my basic understanding of MMSE equalizer, and from this weighting factor. Why we are using this weighting factor? We are using this weighting factor to minimize the mean square error value. So what is this mean square error value? This error value is nothing but the difference in my actual transmitted signal and what is my received signal. Clear? So I will be optimizing this W factor here, and I will use this to multiply with my received component here to minimize this error difference. Okay, so what is my conceptual flow for MMSE equalizer? How this equalizer is acting or playing here? So this MMSE equalizer is first step is to get the received signals or received samples. So received samples will be all the different types of samples. That means current sample as well as previous sample. So we will have all the previous samples also. Why? Because intersymbol interference will cause previous samples to overlap with the current sample because of the delay that is experiencing. Yeah. So now from this received samples, we will calculate the weight. Okay. Now we will calculate the weight means how are we calculating? We are calculating using the autocorrelation factor R and we are calculating using the cross correlation factor P. Autocorrelation means it will amount to how much is the level of intersymbol interference, and cross correlation means what is the error between the received and the transmitted, what is the difference in the signal that I have received. So this will correspond to both the effect of ISI plus the noise that is there. So I will have both the effect here. So this MMSE equalizer will find out these two factors and will calculate the optimized weight value or multiplication factor. Now with this multiplication factor, it will calculate the value of the estimated signal. So estimated signal will be calculated here and we will compare this with the actual transmitted signal and we will generate again the error value. This error value will be further reduced by using the same optimization formula just discussed previous to this. Okay. So if I simply summarize the steps are given here in 6 steps actually. First is to get the sample of the received signal or symbols, all the symbols that are there in the transmission. So what it is getting received at the receiver side, get the combination of all the received signals. Then we have to calculate the weight of that means multiplication factor at the equalizer side. Then we have to find out what is the actual equalizer output using this equation. So we are going to multiply the coefficient with the received signal factors here and we are going to find out the error value. So what is the error value here? The error value is nothing but my transmitted signal with the regenerated or the equalizer output. So this amount of error being generated, we will calculate the mean square value of this error and we will try to minimize this error by using the optimization formula, which is this. Two factors of this optimization formula is autocorrelation and cross-correlation factor. Autocorrelation means what is the amount of ISI here, output signal, and cross-correlation means what is the difference between the transmitted signal, that is your decay, with the regenerated signal, that is your output at the equalizer. So this is my error signal. So it will try to minimize these two factors. Using these two factors, the optimization of the weights will be done. This weight will again be substituted in step number 2 and from step number 3 again this whole process will be repeated. So you will be repeating the whole process till this error is going minimum or almost becoming negligible or zero. Okay, so this is the summary. And if I compare this MMSE with your zero forcing equalizer, so there are some benefits and there are some disadvantages. So what are the benefits basically? So what is the main aim of zero forcing equalizer? Is to completely remove the strong intersymbol interference or strong fading effect. But it does not change the noise factor, rather it increases the noise factor. Okay, so it is suitable only for noiseless channels. So MMSE is, it minimizes the total error. Total error means both ISI as well as your noise. So it will minimize both ISI as well as noise. So it is effective for noisy channels because it can handle noise also effectively. Noise consideration, it does not consider noise effect. So noiseless channel only it is effective. Here it also considers the effect of noise, the error because of the noise. Noise enhancement in zero forcing, noise is enhanced very, very high. But in case of MMSE, there is no enhancement. Noise is handled effectively in a controlled way. Practical performance is poor performance in noisy channel, good performance in noiseless channel. MMSE, better in both the types of channel, both noisy as well as noiseless channel. Complexity, this is having lower complexity. Why? Because it does not have to consider, or it does not have that optimization factor involved here. So we don't have to optimize the multiplication factors. We don't have to go through that 6 steps that I discussed just now for zero forcing equalizer. It will simply use the inverse characteristics of the channel and it will multiply it with the received signal and try to regenerate the output, but the noise will be amplified here. But in case of MMSE, we are using one optimization algorithm. We are trying to calculate what is the amount of ISI, what is the amount of error, and we are trying to optimize the weighting factor. That means the coefficient, multiplication coefficient factors with the amount of ISI and the amount of error that is there in the received signal. So we are effectively, we are doing more amount of calculation, more amount of iteration, more amount of solving. So more complexity or higher complexity is there involved for MMSE equalizers. Okay. So this is the basic understanding of MMSE equalizer. Next, in the upcoming session, next class, we are going to discuss adaptive equalizers, which is also a part of your linear equalizer. So till now, what we have studied zero forcing equalizer and we have studied MMSE equalizer, which is part of your linear equalizer. Now, both of these equalizers are not adaptive equalizers. Not adaptive means what? Not adaptive means when my channel characteristics is always changing with respect to time, with respect to motion of the transmitter and the receiver, with respect to your delay, with respect to your frequency, with respect to your phase, amplitude. So there are so many factors affecting the channel characteristics. So channel characteristics is always varying in time. It is never fixed. So the equalizer characteristics should also be adapting with the channel characteristics in order to compensate the effect of the channel. But in case of the zero forcing and MMSE, both of them are not adaptive equalizer. That means they don't change according to the changing nature of the channel. So we are going to study this adaptive equalizer in our next lecture, in the upcoming lecture series. So we will study this next in our next class. Okay. So this is all that is there for today's class. In my next class, I will discuss on adaptive equalizers, the types of adaptive equalizer, the advantages or comparison of all the different types of linear equalizers. Then we will go to non-linear equalizers, and then we will compare the different types of non-linear equalizers as well.